I may need to log into Slido from a mobile device. And I hope you can access these slides. The URL is posted over here. And I will be monitoring the chat window in the Slido as well. So today's tutorial is on a project that I've been working on for a few years. It's the Extreme Scale Scientific Software Stack, or E4s. And the motivation for this is that as our software gets more and more complex, it's now getting harder to install tools and libraries correctly in an integrated and interoperable software stack. To address this problem, the Extreme Scale Scientific Software Stack aims to provide better quality software with documentation, testing, integration, and a way to deliver the software more easily. We have community policies for products to join the E4s. We have a doc portal that's a single portal to all the E4s product information. We have testing. We have a curated collection where we build these tools, we verify that they are working correctly, and then release them in a curated package. We have quarterly releases. We just had a 2021.02 release, and also build caches. Build caches allow you to install the packages in a binary form, and you can develop these software stacks based on an installation on a HPC system with bare metal install, or you can use the build caches to create custom containers as well. It's a turnkey stack which aims to provide a new user experience. You can download our software from the e4s.io webpage. We are also looking to expand, and our strategy group to include other US agencies besides the US Department of Energy, industry, and international teams as well. So in case you're wondering, what is E4s? It's a curated Spack-based software distribution. E4s provides Spack binary build caches for bare metal installs for a number of platforms. These include x86-64, IBM Power 9 or PPC-64 LE, and ARM64, AArch64 platforms. We have container images available for download on Docker Hub and the E4s webpage of pre-built binaries of ECP ST products. We have base images so you can create your own custom image, and also full-featured containers with GPU support. We have GitHub recipes for creating custom images from base images. We have GitLab integration for building E4s images. We even have a validation test suite so we can confirm that the packages are installed correctly and they work together. So we can sweep across multiple installed packages. And we have validation test suite on GitHub. We have a container launch tool that allows you to substitute MPI in the container in your application with the system MPI if it's using the mpitch ABI. And so you can get near native performance for internode performance for system interconnects. We also have a VirtualBox image which supports container runtimes such as Docker, Singularity, Shifter, Charlie Cloud. So you can install this VirtualBox image, say, on your laptop, and then you can see exactly how these container runtimes work. So we also have AWS images such as AMI that you'll be using for the tutorial today. And we have GCP images as well. I'm looking at the list of participants. Just to confirm, we have do we have a, a large number of participants here, Tasia? I see 6 right now.
I'm sorry, what was the question?
Is it just the 6 participants here, or are we in a separate session?
Oh no, that's just us. There's a separate amount of people. I'm not exactly sure the extent of the number. I'll let you know once I have it.
Okay, I would just like to know how many participants there are so that we can show them the AWS image and boot up additional images if need be. So
okay,
maybe we can.
I can get those numbers for you in the next 2 minutes.
Okay, great, thank you. So we will be seeing an AWS image where you can log into these systems. These are 8 core systems on AWS, and then you'll be able to run the E4s software stack right there and deploy. So there are 3 different areas, technical areas in the exascale computing project. There is the application development, AD, the software technology, ST, which has 70 unique software products. And there is the hardware and integration, HI, which then provides integrated delivery of ECP products on targeted systems at several DOE HPC facilities. The ECP-ST has 6 technical areas. There's a workflows area that has just been added to the. So we have programming models and runtimes, development tools, math libraries, data and visualization, software ecosystem, and the National Nuclear Security Administration's software projects under the NNSA-ST area and the workflows area. So the key theme is that we want to explore the development of new algorithms and software for emerging HPC systems. We have many different packages that are available. And these include some packages that are very widely used in the HPC community, including MPEG, OpenMPI, PETC, Trilinos. There are some new packages that provide performance portability for on-node parallelism, such as Coco and Raja. We have software delivery through Spack. And there are some new products that enable exploration of emerging HPC requirements, such as SICM, ZFP, Unify, CR. The products include MPI, which provides the backbone of HPC applications, OpenMP, OpenACC, performance portability libraries such as Cocos and Raja, and also LLVM. LLVM has emerged as a very important technology for DOE and the rest of the HPC community. And there is a DOE fork of LLVM where many of the projects that are funded under ECP are getting integrated. And then that is available as part of E4s. We have performance evaluation tools such as PAPI, Tau, HPC Toolkit, math libraries, which includes BLAS, OpenBLAS, and other libraries which include Trilinos and PETC, and SuperLU and Sundials. And we have IO libraries including HDF5, MPI IO, Adios, Adios2, data and visualization products such as ParaView. And many of these ST products are then integrated into E4s through the software development kits or SDKs. And if you go to the E4s webpage, you can see the community policies over here for any product to join E4s. And there are a number of these policies. There are 9 policies that are available right now. And these are community policies that have been developed after much discussion. These include policies such as Spack-based build should be there of your package. There's some minimum validation testing. There's sustainability, documentation, product metadata policy, a publicly accessible repository, and then imported software, error handling, and E4s test suite. We have had several releases of this curated set of packages, starting from the first release in October 2018. We just had a quarterly release in February 2021, last month. And this particular release is interesting that it has support for Intel One API and also the LLVM DOE product, which is based on version 13 of Clang and Flank compilers. We'll get to use all of these in the AWS image. So we use Spack as the package manager for software delivery. And you may be familiar with other package managers. Maybe you have used Yum, you have used APT, or used other systems. But you'll see that Spack provides the ability to install multiple versions of the same package and specify versions of software packages that are and are not interoperable. Now, Spack is a build layer, not just for ECP E4s software, but also a large collection of software tools and libraries outside of ECP software technology. It supports achieving and maintaining interoperability between these packages. You can learn more about it from the spack.io webpage. This is becoming more and more important because scientific software is becoming extremely complex. Here is the dependency tree of a package called Nalu. Nalu is a generalized, unstructured, massively parallel, low mark flow application. And you can see the different dependencies. Nalu depends on Trilinos. Trilinos depends on Parmedis, Sweet Sparse, Boost, Mumps, NetCDF, and so on. And so if you want to install all of these packages in an interoperable way, it can be challenging if you do not use a package manager. Now, this complexity is not just for this one package. We are seeing it in all types of packages. This is Deal2, a C++ finite element library. We have RMiner, which is a R data mining library, which depends on all of these packages. And so the complexity just grows a lot, and managing that becomes challenging. Now, this is even true for proprietary codes that are based on many open source libraries. So you'll see that even packages like Aries is now depending on so many other blue colored open source libraries. In this, half of this DAG is external, and more than half of it is open source. So we are building an entire ecosystem of applications. There are over 15 applications in ECP, and then we have over 80 software packages. And with each package, we have multiple target architectures and platforms, and different compilers, and programming models, and versions of each package with their external dependencies. So you can see that clearly this becomes very challenging, and we have, say, over 1.2 million combinations. And every application has its own stack of dependencies. It's reached a point, a crisis point, where there are many FTEs that are just dedicated to building and porting applications at several DOE laboratories, and your experience may be similar. And often what we do is we trade reuse and usability for performance. So we must make it easier to rely on others' software. But how do we install software on a supercomputer? Let's go to the crux of the problem. first you just download all the tarballs you need, say 16 packages that are required for your installation. And then you start building each of these packages. And it looks a little bit like this. You create the directories, you configure it, you make, then you fight with the compiler with the flags, then you build, you tweak the configuration parameters, you again configure, make install, and then once you have installed everything, whether it's with make or CMake build systems, then you create your application that depends on all these 16 packages, and then you run your code, and it could segfault. And so then you start all over again and try to find out where you went wrong and which parameters you need to tweak to get a compatible software stack. And it's reaching a crisis point where it goes beyond the expertise of a user to install the complete software stack themselves. And to help with that, there are different approaches. Now, you may wonder, what about modules? Well, aren't the software packages just available from modules? And there are two modules, the Tickle modules from circa 1995 and LMod from TAC. But modules don't install the software. They just set environment variables, such as path, LD library path, etc., to a package that has been installed by someone else. And so you can only do a module load on packages that have already been installed. So we use Spack because it's a flexible package manager for HPC. Now, how do you install Spack? You can just clone the Spack repo. Here is the URL, and then source the setup-env.sh, and then you're ready to install a package. You can install a package such as tau by saying Spack install tau. Then tau and all its dependencies in the default mode are installed within the Spack directory. But unlike typical package managers, Spack can also install many different variants of the same package. You can target multiple compilers. You could say, please install tau with the LLVM compiler, or with the GCC compiler, or with the Intel compilers. And you can have different MPI implementations, whether it's Intel MPI or OpenMPI or MPage, and then different build options. Now, how does that look? Well, when you clone your Spack and set up your environment script, I recommend that you do a Spack compiler find to set up the compilers. There is a .spack directory. It has a compilers.yaml file where these compilers can be stored. And when you say compiler find, it just finds the different compilers and then stores it in this file, compilers.yaml file in the .spack directory. You can also say Spack external find, and then it sets up external packages. So you don't need to install packages like tar or CMake from source. You can just pick up the packages that are already pre-installed in your system. So that cuts down on the build time. And this is a very important step. You can just say Spack external find and set up the environment. And then you can install your package. If you want to install it directly, one package at a time, you can say Spack install the spec or the package name. And this is unconstrained. It uses the default mode. Now, I mentioned that Spack understands versions. So instead of installing the default version of tau, you could specify a given version and say, please install tau version 2.30.1 by using this @ symbol. Now, @ specifies the version of the software. And then you can also specify the compiler using the percentage symbol. So when you say percentage, it looks for the name of the compiler that it has found in this Spack compiler find command. And then you can say GCC version 730. And then it will use GCC 730 to install this tau version 2.30.1. Now, each spec or each file of a package recipe has some variants. It has variants such as you can say enable plus level 0, and this is a build option for tau. So here, what happens is tau's module for Intel one API level 0 runtime will get installed. And if you are using an Intel GPU, you could get detailed information about the execution of kernels and the level 0 runtime from the tau performance system. You can specify variants such as MPI and even specify which product provides that MPI capability. So when you say plus MPI, you can specify a caret symbol to specify the dependency information. So I'm saying, please use MVAPH2 version 2.3 to satisfy this MPI, and then use the without wrapper RPath or a tilde wrapper RPath. So there's plus and then there's tilde to specify a negation operation. So you could go to arbitrary level of detail and specify specialization of a particular build. And you can have multiple builds of the same package. The spec syntax is recursive, so you have full control over the combinatorial build space. Now, once you install the packages, you can say Spack find, and it will show you what packages were installed. This is a Power 9 PPC64LE installation, and you can see Trilinos version 13.0.0 is installed. You can have multiple versions that can coexist. Multiple versions of the same package are okay. And so it's possible to have different compilers supported in this manner. And here, packages are installed to automatically find correct dependencies. So when you say Spack load a package, you can say Spack load minus R or recursively Trilinos. So you could say Spack load minus R Trilinos, and it will load Trilinos and all the dependencies that were used to build that version of Trilinos. Now, the interesting thing about Spack is that it also generates module files. So you can also use module commands to load the package, like module load Trilinos, and you may be all familiar with the use of modules on your HPC systems. So Spack simplifies HPC software for users, for developers, for cluster installations, and the largest HPC facilities now use Spack. You can learn more about Spack from this web page. Spack is central to ECP's software strategy, and the roadmap has many features. You can learn more about it at this web page as well.
Hello, Samir. I was just wanting
Yes.
to let you know we had a couple questions in Slido if you wanted to have a look at those and see about answering them.
Yes. Does this mean Spack will replace our current way to use modules on HPC? Well, I should say that Spack provides modules. So if you have a Spack-based installation, you can continue to use modules. You'll just see those modules coming from the Spack installation. Does that answer your question, Vemi? And what does Spack pull source when downloading? Is it GitHub, or Spack hosts its own source code repository? Well, that is up to you as a package developer to specify in the package recipe. So you can say the Spack recipe has certain paths, and it can specify a GitHub location, or it can specify a location of a certain package. So here, for example, if I say which Spack, let's say Spack edit a recipe like Trilinos, then this recipe will contain information about where to get Trilinos. And you can see over here that there's a home page specified, there's a URL with the release, and then various versions with their SHA sums. So the MD5 sum is specified here. And then you can specify any arbitrary version. So even if there is a version like 13.1, which is not there in this recipe, it knows that it can go to this URL and try to get Trilinos release 13.1.tar.gz. If it does not find it, it will report, Or you can specify the Git repo and you can say develop or master, and then it will pick up from Trilinos by doing a Git clone on the Trilinos repo, and you will be able to see what the version that you request. And here in this recipe, you specify what variants to provide. For example, what kind of floating point operations, Fortran support, Adios to HDF5, and these variants can be then used to then enable certain features. Like if I said variant is SuperLU, then I could say Spack install Trilinos plus SuperLU, like this, and then it will pick up the details of that, and then I can specify a particular version, like at 13.1, like that. Does that help answer your question, Vivek? I see that the question is answered. Great, let me continue, and feel free to ask questions as we go along. And so our software technology area has software development kits from a number of different technology areas. These include SDKs for the original math SDK, also known as the X SDK, which includes packages like Trilinos, Sundials, PETC, SuperLU. We have programming models and Runtime SDK, and I lead this PMR SDK, which has packages like Legion, Cocos, Raja. Cocos is for node level parallelism, the X in the MPI plus X. We have MPage, OpenMPI. You may be all familiar with these for using the internode communication. We have support for compilers, including LLVM, and a number of different projects, including Flag for the Fortran compiler. We have tools and technology, which includes Tau, HPC Toolkit, Dynenst API, and so on. We have visualization tools such as ParaView, VTKM, Ascent. We have data management, IO checkpointing services, such as Scalable Checkpoint Restart. We have Feudel, ROM.io, HDF5, Parallel Net CDF, Adios. We have tools in the ecosystem, E4s at large, which include the GeoPM and the NRM and Argo containers. And these are the different SDKs. We also have XRWorks, which is a workflow SDK, which has recently joined the ECP software technology. And in all of these cases, we develop the package, then we build it, we test it, we deploy it for different SDKs. And then there is an integration stage. We have the build, test, deploy, integrate in this E4s ECP-wide software release based on SDKs. So you can learn more about this at our e4s.io webpage.
Hello, Samir. We have another question and a comment in the Slido.
I see that. What does, let me just update the Slido. Does Spack use makefiles provided with the package to build, or is it something that replaces makefiles like sconce? Spack can use the recipe that is specified, and this includes use of makefiles, autoconf, configure scripts. It includes use of CMake. So it can use whatever a package normally uses to build it, just that it will be installed using the Spack commands, which will then spawn the configure and make. So it will still use make files to use to build that. Does that answer your question, Alexander? And you list parallel netcdf and HDF5 as IO packages, but you don't list netcdf itself. Well, netcdf is also available, and yes, it's part of the Spack recipes, so you can install it. And is that does that answer your question? Okay, good. And thank you for stopping me about to check the questions. I'm seeing the questions on my phone while I look at this. So there are different components. E4s is a curated release of ECPST products that are based on Spack. And we have build caches so that we can support bare metal installation at facilities and even do custom container builds. We have support for x86-64, PPC64LE, and ARch64, ARM64 platforms. And you can pull these container images from Docker Hub and E4s web page of pre-built binaries of E4s products. Now we have also base container images which allow you to create a custom image. And we also have full-featured containers with support for GPUs. So if you wanted to do a facility-wide install, you could just download a single file or a single container and then have it installed for everyone. And there are different container runtimes that I'll talk about, including Docker and Singularity. Now we have GitHub recipes for creating custom images from base images. We have a container launch tool that can be used to substitute the MPI in your application binary at runtime with the system MPI. So if your application uses libraries from the container and you want to, and you're using, say, mpage based build of your application, and you may have, say, Cray MPI or Cray mpage installed on your system, and that uses optimized communication primitives for internode communication using high-speed interconnects, and you want to use that, then this E4s CL will allow you to substitute the MPI in the application with the system MPI. And it simplifies the workflow. I'll talk a little bit more about this later. We have a validation test suite so that you can not just install a package, but you can do a build of an example typically taken from that package and do a build of that application. You run it, verify that it passes or fails. And then we also have GitLab continuous integration or CI facilities to ensure that packages can be built. And we have support for the Spack pull request testing through GitLab. So E4s provides all of these things. We also have a doc portal where we summarize the documentation and metadata of the packages that are there in E4s. We do this by raking the product repos. So every night it goes out and we pull in the latest change me logs and the change logs, the README files and other product descriptions, and then populate it on the single doc portal page. We have a AWS virtual, an E4s virtual box image where we have support for container runtimes. And if you're just getting started with the use of containers and you want to see the differences between the different runtimes, this is an easy way to start, and you can see the Docker, Shifter, Singularity, and Charlie Cloud runtimes. We also have an AWS image to deploy E4s on EC2. And this is what we will use in the hands-on session today. Yes, we have booted up a number of images, and our hope is that you can either share or have a single image for each of you, and each instance will have the full E4s stack, and you'll be able to use it through a SSH session or through a web interface for 3D graphics. And so we also have a GCP image of E4s. Now, if you're wondering, what are containers? Well, containers provide a lightweight collection of executable software that encapsulates everything needed to run a single specific task. If you want to nail down the environment and have a reproducible software stack, then containers provide a viable approach. They have everything that your application depends on except the operating system kernel. They're based on Linux. All the processes are user level processes, and the software is isolated. So it provides a portable solution, and you can think of it as chroot on steroids. Docker is a very popular tool for deploying containers. It's available on all major platforms and it's widely used in industry. You can download containers from Docker Hub, and we will go through a step-by-step process in the hands-on session later, and we will see how to create a container, how to use a container, a simple container with Docker. Now, in case you are wondering, how does this differ from virtual machines? With virtual machines and solutions like VirtualBox, you have a full operating system within the VM. And there are different types of hypervisors where you can run the hypervisor directly on the hardware or on the operating system. But if you deploy a virtual machine, it has its own operating system. So for example, you could be running on your host, say Red Hat Enterprise Linux 8.3, and then you could launch a virtual machine which has Ubuntu 20.04. So both of the operating systems are here, and there's this added overhead of your application running on the operating system like Ubuntu, which is then deployed on this particular host operating system. But with containers, you get rid of the operating system. The container does not have any OS. It just has the libraries and the applications, and it runs natively on the same operating system. This is a very important difference between virtual machine-based approaches for encapsulating software and container-based approaches. And so the performance of container-based solution is much better. And this can have a major impact on the way you design software and distribute your software with containers. So we'll look at how you can create the containers, how you can use containers that come from the E4s project. And if you go to the download page in the e4s.io, you will find different operating systems supported. You'll see images such as this one, x86-64, which has CUDA and ROCm, PPC64LE, and you can just do a Docker pull directly or download an image from here. And if you launch that image, you'll be able to see that there are a number of packages that are installed in that image. So here is Adios, Feodel, you have Caliper, Argobots, HDF5, all pre-installed. You have HPC Toolkit, Cocos, MFEM, MPitch. So you can just say, Spack load MPitch or module load MPitch, and it will just put this in your environment. So the release that we just did, 2021-02, is a GPU release. It has 67 and more ECP ST products. It has Ubuntu 18.04, and it also has AI and ML packages with support for AMD GPUs. So you have TensorFlow 3.5, 2.3.5, you have PyTorch 1.8, you have HoroWAD, and the HoroWAD uses the MPI, which is there in the container. So you can have a fully accessible AI ML software stack along with the HPC components all in one release. Now we have support for GPUs, including ROCm for AMD GPUs, NVIDIA, CUDA, and it ships with these runtimes. So what is interesting is we have support for all three major GPU vendors, including AMD, NVIDIA, and Intel. And we have Intel One API with Intel compilers and Intel MPI and Intel AI Kit with the AI ML software, all bundled together. We also have Cocos with support for AMD GPUs in this distribution. You can see different packages like OpenMPI or PAPI or PETSI or Strumpack, Tau, Trilinos, and these are the locations where they are installed. You can also download a single image. such as the singularity image, and then just run it. So all you have to do is say wget or go to this page, get this one single file, and then say singularity run ecp.simg. And then it will launch this image, and you will see the full set of packages and use modules or Spack commands. Now, I mentioned that this image supports Intel One API, CUDA, and ROCm. You can say Spack find, and it will show you. And we also have support for PPC64LE, or the IBM Power 9 platform. It's used for systems such as Summit at Oak Ridge and Sierra at Lawrence Livermore National Labs. And you can get this image directly from the Docker Hub. It has support for CUDA. You can pull it like this, the same command for x86-64 and PPC64LE. And there are these 67 products in the Power 9 PPC64LE Singularity container as well, like Adios and Ascent, Argobots, Gasnet, HDF5, Cocos, Hyper, MFEM, MPitch. You see PDT, PAPI, Qthreads, Raja. We have Strumpack, Sundials, Super LU for LU solvers, Trilinos, Turbine. Now, these packages typically take a long time to install, and they are all available in this binary form, ready to use. We have this singularity image for PPC64LE as well, where you can say singularity exec, and then you can specify the --NV flag. Now, this --NV flag stands for the NVIDIA support for CUDA, and it pulls in the CUDA libraries that are there on your IBM system into the image, and so you can run your applications directly with the IBM image, and then use the GPUs directly from within the container. Here is an example of using the image, the Power PC image, and I'm just launching Python. That's there as the default, and you'll see that it has the AI/ML stack already integrated. I can say import TensorFlow or Torch for PyTorch, or CV2 for OpenCV, or even other packages like Matplotlib or NumPy. And you can say TensorFlow test is GPU available, and it shows you that it can access these 4 V100 Tesla GPUs. So you can launch your GPU-based computation. You can use TensorFlow with access to GPUs, all from the same image. Now, if you had to install the image or these components yourself, presumably it will take a bit of an effort to find the right options and figure out, how do I enable support for a GPU in this Python package? How do I build it so that it can access that GPU, install it in a location that I can access? And it just takes a lot of effort for you to do all those steps. Instead, you can just download a single container, a single file, and then you will have all of these packages pre-installed in an image for you. We also provide container images as base images, so you can build your own custom image from the base image. Now, why is this interesting? Because if you download container images from E4s or from the NVIDIA website, the NVIDIA Cloud NGC, NVIDIA GPU Cloud website, then you will see that by default, those images understand how to use GPUs. There are some flags that you need to enable for a container to be able to access the GPUs. And if you just build it from a scratch from your own image, you might be missing out on some of those flags, the secret sauce to accessing the GPU, which we have figured out. So you can use a single container image that we provide, say a singularity image, and it will run with all 3 GPU vendors. So you can have Intel GPUs or like a Tiger Lake GPU, Tiger Lake processor, which has a Gen 12 LP GPU, and you can run the one API DPC++ completely from the stack. Or you can have ROCm for AMD GPUs or CUDA 11 for NVIDIA GPUs, and they'll access the GPUs from that container. So you could start with something that already works with these GPU runtimes. And you can choose from base images. If you want to create an optimized image, you can start with the base images provided by ECP E4s. We have UBI, or Universal Binary Interface. Now, this is a very interesting product from Red Hat. If you pick a base image which is based on UBI and you run it, you run your container with many different packages on a Red Hat Enterprise Linux system, then your software, the UBI-based container, is supported under the Red Hat license. And so you can get support for that UBI image through Red Hat, and whatever runs on it with UBI on a Red Hat system has that. So when you look at the UBI images, you should note that. We have recipes that show you exactly step by step how you can work with a Docker image. And you can say, please start from this image, which is the ECP E4s for the Ubuntu 18.04, based on Spack x86-64 and a version. And then you can specify a working directory. You can have a spac.yaml file. A spac.yaml file is a manifest of all the packages that you want installed with the full environment. So you could say, I want to use this compiler, GCC 7.5. I want to use MPitch 3.2, and then specify those versions in the spac.yaml file. You copy this over in this Docker file. This is a single file called Docker file. And then it says Spack install, and then Spack clean and remove this. And then that's the work directory. So these Docker files are all there. Excuse me. And you can see for various platforms, for various operating systems, how it looks like. So these are packages.yaml, spac.yaml files that you can then look at. And this is how a spac.yaml looks like. You can specify the E4s packages. Here is a Docker recipe. This is the web page. You can see that we have Slate, Magma, STC, Hyper, MFM, all of these packages. Now, if you don't need all of these packages, you could just prune this list and start with just say maybe 5 packages. You could say, I am interested in PETC, I'm interested in SuperLU dist, and I'm interested in say Adios and nothing else. So you can just edit this list and then take this as a starting point, and you could just say spac-e dot. So the directory where the environment file is, where it has to pick up the spac.yaml, and then install. So spac-e dot install will allow you to install on bare metal. Now you can speed up this installation by pointing to the build cache, and then it will just download binaries if it gets the right set of compilers and the runtime. Or you can make a Docker build. You could just say Docker build with this and dot, and then it will pick up the Docker file where you'll be able to specify what steps need to happen. So you could say Docker build in this current directory dot and give it a tag. So this will be the tag or the name of your Docker container. And you can even say don't use the cache. So here is the Docker file. It specifies the spac.yaml, which specifies what packages are to be installed, and then it will create it for you. Now, in the hands-on session, I would like to show you how to create your own Docker container. And we'll have everyone log in and try and do this over there. Now, in case you were wondering about the build cache and how do I use it? Well, you can just follow these commands. You can say spac mirror add the E4s with the cache.e4s.io, download this public key, and then say, I trust this key, so that you can download packages from this repository. You may have used similar things for the Yum repos for Red Hat. Now, in this this cache.e4s.io, we have binaries for different versions of the package. We have binaries for different operating systems such as CentOS 7, 8, Red Hat, Enterprise Linux, Ubuntu. We have for 2 different architectures right now, PPC64LE and x86-64. And as you can see, we have over 37,000 binaries in our mirror. If I click on a package like Amrex, it says Amrex 2103. There are also earlier versions. So this is from March 2021, the latest one. And you can see we have this continuous build process where we have uploaded these binaries. So this is for PPC64LE architecture for Red Hat Enterprise Linux 8 with the compiler 831. And this is the hash. This hash is used by the Spack concretizer to match. So if you have a Red Hat Enterprise Linux 8 with PPC64LE with GCC 8.3.1 compiler, the Amrex 21.03 will have this hash. And if this hash matches what your environment is, then it will be able to download this particular binary and then install it locally. So you will not need to build from source code any of these packages. You could just point to this and speed up your install by using the Spack build cache. So in short, a build cache is a collection of pre-built binaries for certain compilers, for certain operating systems, for certain architectures. And then you can just say Spack install Amrex at 21.03. And if you have done these steps, it's going to look in this mirror and then download it. Now, what is interesting is that you don't need to go to the website and access the mirror. You can also create your own mirror. And yes, you can put it on any web page, or you can put it in a file system. So you could have one mirror, a local build cache that will then pick up the packages from your local file system for everyone to use. And this is what is done with some ECP applications. Here is the WDM app web page. And to speed up the installation and installing on the software, this full software on this system required several hours, and you could just speed it up by just saying, get this key, trust it, add this mirror, and then just install it. Or you can have a Docker container where you can pull it from Docker Hub with this optimized container for the WDM whole device model application. And then you can run it like this. When you say --rm, it should be double dash in an interactive way. It will then clean up after itself after that image is no longer used. We also have the Pantheon application, and it also uses the E4s build cache to support these workflows. We can learn more about it and how they are using it on the Summit system at this web page. Now, they have realized speed ups of 10x in installing their packages, and it just takes, in some cases, just a couple of minutes to install the full application. Now, in our hands-on session, I also have a build cache, and I will illustrate how you can use that build cache to install a full ECP application and compile it and then run it within the AWS system. Here is a validation test suite. Now, I mentioned that it's not just important to build these products and send the binaries. We also want to make sure that the tests associated with that package pass. So we have this validation test suite. Every package directory like this Magma has a clean.sh, a compile.sh, run.sh script. So you can clean and build the application. When you run it, it will use MPI, it may use MPI run, and it will launch the multi-rank application, and then you'll be able to see whether it ran properly or not. So this allows us to sweep through a collection of packages and verify that they all work before a given release. We also have a new LLVM validation test suite for the DOE fork of LLVM. And we have reproducible container builds. Now, I showed you an example of the E4s build. Here is a build for a custom product like SuperLU. And for supercomputing tutorial, they were using this for their environment as a container. So they wanted just SuperLU dist, PETC, MFEM, StrumPack, ButterflyPack, and OpenBLAS. And just these packages. They didn't want the bulk of all the packages that the E4s container provides. They could specify compilers such as, I want to use GCC 730. I want to use to build, I want to use support for MPI, where MPI is provided by MPitch. And then you can see that the provider of MPI is MPitch, and MPitch is version 3.2.1 without the wrapper RPath. This argument is important to create binaries that can allow substitution of MPI with the system MPI. And then the GCC over here is specified over here. And then it will build it. How does it build it? Well, you start from a base image like this. You have this Docker file, and then you run the script for Docker build, and then it will execute the commands in this to create a container, and you give it a name. So you say Docker build, here is the name of the container in the current directory dot, and then it will read the Docker file. It will go through these steps, and then it will create a container. Now, once you have that container, you can then push it to Docker Hub if you like, or then you can just run that Docker container image, and then you will have the environment that is created by the installation of all of these packages over there.
Hello, Samir. We have a couple
Yes.
questions in the Slido.
Okay, let me just refresh the screen. So with CentOS 8 support ending soon, will software compiled on other operating systems be provided? So even with CentOS support ending, I believe that Red Hat has a path, and we will have UBI support and CentOS support going forward. And we also have Ubuntu. David Rogers says, I've heard that the E4s build cache is amazing and transformational. How difficult would it be to replicate, for example, to set up and administer a build cache for Apache Software Foundation? What about adding a new CPU or GPU processor target architecture to the existing cache? These are excellent questions. I should mention that this build cache, E4s, is a build cache for Spack. That's a very important thing. This is a build cache not for any package manager, but specifically for Spack. So if your Apache Foundation products were using the Spack package manager, and they were building with Spack, with recipes integrated in the Spack, then absolutely we could add support for those packages, build them, push them to our repo, and then when you say Spack install a certain package from Apache, it will then pull in the binary from our build cache. Now, as far as adding support for other architectures to the build cache is concerned, that's a very good question. We just need to have access to that processor architecture, and then we can build on it. We have GitLab servers. We have GitLab runners that are running at the University of Oregon, building for different architectures. And so we can add support for other architectures. And in fact, we'll soon have support for the A64FX processor. And we already have support for GPUs in the x86-64 and the PPC-64 images. Does that help answer your question, David? Okay. And thank you for asking those questions. So here you can see how we could start with this set of packages, and then we can create the Docker file starting from something that's already there, and you can just tweak it to your needs, and then you can create a Docker image, and then you can run it on your system. Here are all the runner images for Red Hat and CentOS. And you can see how our GitLab CI build pipeline works. We have all of these architectures building from GitLab, and then you can see the progress. You can click on a particular build and see which packages were there, and they then push these packages to our build cache. And we also have runners on the Frank set of systems at the University of Oregon, an aggregation of machines called Frank, Frank for Frankenstein. It's a set of monster machines. You can see that it has tags for GitLab GPU runners. We have tags for, say, A100, Intel DG1 for the discrete graphics 1 GPU, and MI50 from AMD. So there are different runners. You have tags for x86 64, and these systems can be used for the general build pipeline. They are runners that are created for getting these jobs. Now, this is not just at the University of Oregon, but various DOE labs have GitLab runners. And here is the E4s build pipeline, the E4s pipeline running on Cori at NERSC at Berkeley Lab. And here is the GitLab build pipeline for the build cache at Oak Ridge National Labs on Ascent. This is on a PPC64 LE. You can see how they are building E4s binaries. So you can create your own local build pipelines. You can have your own local build cache. And so if a person is trying to use, say, HDF5 on a Ascent or Summit and pointing to their local build cache, then they'll just pull in the binary and they'll not need to recompile HDF5 from a scratch. Then again, you can, of course, use the validation test suite of E4s to make sure that HDF5 was correctly installed. It will run a test case with, say, 8 MPI ranks quickly, less than a minute typically, and show you the pass-fail that the example builds and it runs. So it gives you some confidence. And with confidence, we have certain CI badges that are now available for the E4s project for different products. So you can see what badges it has with the build passing and so on. And you can look at these badges. Now, if you want to look at all the different products that E4s has, there is a doc portal which provides a single online location for accurate product information. And we rake the repos every night and extract the data, capture this data, and then put it in the doc portal. And you can search for different packages. You can expand it to see the name, functional area, the change log, the README files that are all pulled in every night from the product repos from their GitHub sites. And you can search for it. You can look at the area description. We also have a virtual box image, which has container runtimes from Singularity, Shifter, Docker, and Charlie Cloud, all integrated in a single image. So you could run this virtual box image on, say, your laptop to learn more about the different packages, learn about Spack, to learn about these container runtimes. And of course, the E4s CL tool, which is now available in beta testing at this website. You can clone this repo. And the idea here is that it's very cumbersome to replace the MPI libraries. And you have to learn a lot about the environment. You have to set LD library paths. And this is just a simple tool where you can say, initialize my environment. I'm going to use this MPI, this Singularity runtime. This is the location of the MPI directory. And then it will extract that information. It will create a profile. It will store it in E4s CL database. And then instead of setting those paths manually, if you run your application as MPI run and a.out, you could just say E4s CL MPI run a.out, and then it will go look at those paths. It will set the LD library paths appropriately. So you'll be able to mount the local file system in the container image with Singularity, and then you'll be able to use the host-based MPI libraries. So if you have, say, the Cray MPage or MVAPage2 with InfiniBand, and you want to use that InfiniBand adapter between the nodes, you will be able to substitute the MPI at runtime with the system MPI. So you don't need, so you can build an application with, say, MPage configured the right way, which is the default for the E4s containers, and then you'll be able to just substitute that MPI by this simple command like this. As I said, this is a product that is still under development, but friendly users are welcome to try it from that GitHub webpage. And this is the architecture for how it launches the application and the libraries. So in summary, I would like to just say that E4s is not a closed system that's just taking contributions from DOE software teams. Rather, you should think about E4s as an extensible open architecture software ecosystem that accepts contributions from US and international teams. It's a framework for collaborative open source product integration. It's not a monolithic take it or leave it software behemoth, but a full collection of software capabilities and a manifest for a la carte selectable software capabilities. It's not a commercial product. Everything is available in an MIT license. It's a vehicle for delivering this high quality reusable software products. And it's not just a simple packaging of existing software, but you should think of it as a conduit for future leading edge HPC software targeting scalable next generation computing platforms. And there's still a lot of work that we are doing in the areas of support for GPUs, visualization tools, LLVM, continuous integration testing, facility deployment, startup, scalable startup, improving the launch of MPI applications using E4s CL, creating binary build caches, and our Singularity Docker images. So our vision for E4s is that E4s has emerged as a new top-level component in the DOE HPC community that enables fundamentally new relationships, and there is potential for interaction with other US agencies, including NSF, the Department of Commerce, DoD, US industry, international collaborators. NSF and UK are examples where we already have some relationships and we are in active collaboration. The E4s portfolio can expand to include new domains like ML, AI, lower level components. It can provide and aims to provide better, faster, and cheaper capabilities through this software stack. So much of this research is carried out in our performance research laboratory at the University of Oregon in Eugene, Oregon. I direct this performance research lab. This picture was taken before the pandemic. It doesn't look like this right now, but we are hoping for, again, our active visitor program to be there once the pandemic is over and we can return to the campus. I would like to thank our sponsors, in particular the US Department of Energy, Argonne National Labs, Office of Science Contracts, the SIDAC, LBL, Livermore, Los Alamos, Sandia, Battelle, PNNL, and Oak Ridge, Department of Defense, National Science Foundation, NASA, CEA, France for TAO, AWS for providing support for tutorials such as this, where we can launch multiple instances of E4s and show you in the hands-on session that will commence after the break. And the Exascale Computing Project for their sponsorship of the E4s project.